We're going to continue on with chapter 3.3. We're going to look at 0 as an exponent and then end on orders of operation. So something to think about. Let's say, again, you're teaching upper elementary school grades, and then you end up to the situation of something to the power of 0. And then you tell students, well, that just equals 1. But a student says, volunteers that they think it's 0, right? Since it's a shortcut for multiplication, 4 times 0 times should be 0. How do you respond, right? And so in order to respond, you need to understand why it makes sense to define that a to the power 0 equals 1. And so looking at that right here, how come anything to the power 0 equal 1? Well, one way to look at it is to kind of look at a pattern. We're going to base that reason why we define it that way, right? In definitions, we just say it is. In that, looking at a pattern here, we can say 4 to the power of 3 equals 64, 4 to the power of 2 equals 16, 4 to the power of 1 equals 4. And so just looking at a pattern here, as we here, what we're doing is we decrease the exponent by 1, right? What happens here as we decrease the exponent by 1, it looks like what we're doing is we're dividing by 4, right? Because 64 divided by 4 is 16, 16 divided by 4 is 4. So as you decrease by 1, we keep dividing by 4. And again, that's then again because of the opposite of exponents being to multiply, right? But now we're increasing the exponents, you would multiply, but as we decrease the exponents, we're dividing by 4. So the only reasonable answer, if we think about it, we're dividing by 4. 4 divided by 4 equals 1. So it makes sense to say 4 to the power of 0 equals 1. And so that pattern would emerge in any values that we do. So if you say 2 to the power of 4, that equals 16. 2 cubed equals 8. 2 squared equals 4. 2 to the power of 1 equals 2. Then from the pattern, you would say it's dividing by 2. You would say it's 1. So now 2 to the power of 0 seems reasonable to say it equals 1. Now let's take a look at another way, some algebraic way here. Going back to rules of exponents. What is 4 to the power of 3 over 4 to the power of 3? Well, one way to think about it, well, that's just 64 divided by 64 equals 1. So now we see here that 4 to the power 3 over 4 to the power of 3 equals 1. Okay. Now another way to think about 4 to the power of 3 over 4 to the power of 3 with rules of exponents is to say, oh, that's just subtract. You get 4 to the power of 0. What should that be equal to? Well, 4 to the power of 0 should be equal to something, and the rules of exponents say to subtract, and we now know that 4 to the power of 3 over 4 to the power of 3 equals 1. So we should then reasonably say that 4 to the power of 0 is equal to 1, based off of this conclusion here. And so this would follow here from an algebra perspective, saying x cubed over x cubed, the same thing divided by the same equals 1, right? X cubed over x cubed is also x to the 0. We know that because of subtracting. So then what happens is the conclusion that x to the power of 0 seems reasonable to define that equals 1. And so that's our explanation of why we define a to the power of 0 equals 1, as long as a does not equal to 0. And so that leads to the other question then of how come 0, what is 0 to the power of 0 equal to? And so looking at a pattern also, it makes sense. Look at 3 to the power of 0 is 1, 2 to the power of 0, that you would think that it equals 1. That seems reasonable. But then we say, what's 0 to the power of 3? 0. And then it makes sense that it equals 0. And because if you look at those two, there are two reasonable answers for 0 to the power of 0. We will say that it's not defined. We just don't know which one is it, which one makes more sense. In this case, we're just going to say it's undefined or not defined.